relationship between them. This table, as we said before. So I don't talk about this watch anymore in class. Today I will focus on the topology table of EIGRP. Let's take a look at its topology table. In this table, let's just focus on 4.4.4.4. Everyone can see. In the entire topology table, it seems that there is only one address for the next hop. 12.1.1.2. Actually, R1 goes to 4.4.4.4. Both the upper and lower roots are available. But now in this topology table. But only one. So what is the reason? I told you before. There is another command. Add all links behind. Then this is not a real topology table. If you suffix this command with all links, it will show all physical connection table now. That is, as long as there is a way to go, it can show up here. So let's check out all links. Let me zoom in on it. Everyone can see. Above is a topology table. Below is the topology physical connection table. The difference between them is that if R1 now goes to the root 4.4.4.4, there is only one next hop in the topology table. 12.1.1.2. But in the physical connection table there are two. One takes R2. One takes R3. Then the question we think about is, if now the following line does not appear in the topology table, how do we put this line also into the topology table? Let's study this problem together. Only one root is displayed in the topology table. Then the root below is not included. We mentioned a thing last class. Feasible condition. Not all links will be put into the topology table. If you want to enter the topology table, feasible conditions must be met. Feasible conditions are what we call backup lines. AD. The advertised distance. It should be greater than the FD of the main line. For now, it will appear in the topology table if it meets the feasible conditions. It doesn't show up now. Certainly it does not satisfy the feasible condition. We judge whether it satisfies the feasible condition by looking at this parameter. Everyone please pay attention. Now there are two parameters in each parenthesis. The front one is FD. The latter is AD. So now for the main line. Its FD is 435, 200. This is the FD of the main line in the feasible condition. So now the AD of the backup line is here. We want the lower line to be the backup line. So this is its AD. It is 297,856. This is the AD of the alternate line in the feasible condition. Then logically speaking, the feasible condition should be that the AD of the backup line is smaller than the FD of the main line. But now, obviously it doesn't satisfy the condition. So we have no way to add it to the topology table now. That's why it doesn't show up in the topology table. Because it does not satisfy the feasible condition. Then R3 cannot be a feasible successor router. It has only one way to go. We found out now. If it is not in the topology table, then according to what we said in the last class, it is impossible to achieve second-level switching. If there is a problem with the upper line now, since it is not in the topology table, EIGRP is to be recalculated. The line will be recalculated. Then go down the line. It can't be achieved. As long as there is a problem with the upper line, the lower line is switched immediately. It can't be done. So how to change R3 to the successor router of R1? What we're talking about is the AD of the backup line. That actually. Now this is a backup line. This is its AD. Remember the concept of AD? Advertised distance. That is the distance from the successor router to the target network. So it's actually this paragraph. If now I'm going to see the FD of the main line. Feasible distance from R1 to target network 4.4.4.4. That is. Below is actually this paragraph. The above is actually this paragraph. So we want to make the distance below this section smaller. The distance above is greater. As long as I change the value of this section to be smaller than the value of the above section. That's it. In this way, the feasible condition can be satisfied. This place we just saw. If I remember correctly, it should be 435,200. This is its value. This is 2297856. In short, I want to change the value below to something smaller than the value above. Can satisfy the feasible condition. Then we will modify it next. Then the first thing to change must be its metric. How is it modified? How did the metric come from? It is based on these 5 parameters. But usually, we seem to only change bandwidth and latency. We only refer to these 2. And everyone can see. There is a formula under it. This formula is the daily calculation method of metric. 256 times 10 to the 7th power. Divide by the link minimum interface bandwidth. Plus the sum of link delays. Divide by 10. This formula is a bit more complicated. It's okay. Let's do a calculation on it later. After the calculation is completed, we can know how this parameter is obtained. Let's calculate this number. Like the 435,200 we just saw. Then let's study. What is the minimum link bandwidth? Let's look at this picture. Let's do the math first. R1 reaches 4.4.4.4. How is the 435,200 of the main path calculated? Then before we calculate, everyone should know. How did this route come through? There is a 4.4.4.4 route here. Then if you want R1 to learn it in the end, what is its transmission direction? First of all, it needs to be transmitted to R4 through this loopback port. It must be an interface of the local. It is equivalent to passing through this interface. Through the local loopback port. This is a hop count. Then pass it to R2 here. The interface of R2 also received this route. So actually, it also goes through the E01 interface of R2. After a loopback 0 here. Passed an E01 here. Go down and pass an E00 here. That is. 4.4.4.4 first enter R4 from the loopback port. Come out from the 00 interface of R4. The E01 interface passed to R2 enters R2. Then come out from the E00 interface of R2. Pass to the E00 interface of R1. This is called routing transfer. Then all the messages passed. They are all transmitted through the update message we mentioned earlier. Don't forget this. And I told you before. Transfer of routes and transfer of business traffic. Actually it's 2 different things. For example, I'm going to ping 4.4.4.4 from R1. This is business traffic. But what we're talking about today is the delivery of the route. So what does the link minimum interface bandwidth mean? Actually, it means now this route passes in the direction, the one with the smallest bandwidth, of the incoming interface of all devices. What everyone understands may be a sum.